Welcome everyone to a new meeting of new reference and group theory and geometry categories. Our speaker today is Victor Saunier from Bielefeld, and he'll be talking to us about a model for the assembly map. Sorry, a model for the assembly map of bordism-invariant functors.
Thank you very much for the introduction and the invitation. It's a pleasure to be here chatting about this in front of you. So this is joint work with Jordan Levin and Guglielmo Nocera that we did back when I was in Paris. So what is this about? So the title is a model for the assembly map of bordism-invariant functor. And so I kind of want to start by breaking down all of the things and talk to you a bit about, about the the assembly map of localizing invariant. So let's start with a functor from C to D. C and D have all the colimits that you could want, and you have some diagram in C. Then you can first either take the colimit of that diagram and apply F, or first apply F everywhere and take the colimit. You have a canonical map that goes from the colimit of the F x alpha to F of the colimit. And of course, right, preserving this colimit is exactly sending this map to an equivalence. In particular, you can start with a group G, pick a point in your category C, and consider the constant BG index diagram in C with value x. This is the functor that sends just the point. BG is a category with one point, right? And G has its endomorphisms. This is the constant functor. It sends x to the point and everything to the identity. And I can take the colimit of that. This is something that I want to write BG tensor x. And I have a map from BG tensor f of x to f of BG to f of BG tensor x. And this is something that I want to call the G assembly map of f at x. Now this is something that works fine one categorically, but I want to do everything infinity categorically. And if I work in this wonderful land of infinity categories, I can do this way more generally. I can pick a space, so a homotopy type, anima, whatever you want to call it. Look at the constant functor equal to some x in my category, and either apply f before or after taking the colimit. This gives me a assembly map functor for this, and it's better than this, right? In this higher world, what's the left-hand side? It's the unique functor. It's functorial in K, and it's the unique functor which preserves colimits and sends the point to f of x. Now, in particular, if you happen to map to a stable category, then it also is it sends. I mean, in a stable category, pushouts and pullbacks are the same, and so all of the squares are pullback squares, and so you are a homology theory. So this assembly map is trying to compare the homology theory of f of x and f of the homology theory. So it's the universal way to approximate your functor f by a homology theory. And so the functor from which assembly is very interesting, right, and should tell you something, is just those where the functors themselves do not preserve the colimit. Otherwise, the map is just an equivalence. There's nothing really interesting happening. So what are the functors that I'm really interested in? It's Waldhausen's A theory, right? It's a functor that takes a pointed space, and in the modern language takes the K theory of the ring, which is the sphere adjoint loop X. I mean, there are other models for this that are a bit old school, but I really like this. And more generally, right, I have the right to take, if I have a stable category, it's algebraic K theory, and for me it will be the non-connective version. This is something that lands in spectra. It's a functor from cat X to spectra, preserves not that many colimits. And I will also, like a very important example for us will be L-theory. Now, I don't really want to tell you just now what kind of functor it is, because this will be part of the talk. But if you know what quadratic L-theory or symmetric L-theory is, these are examples that will show up. And more generally, I will be interested in the case where F is a localizing invariant on some category that has a good notion of being localizing. So what's an example of what happens in the case of K-theory? So if you start with a stable category, then K3 of S1 tensor C, right? This is this like constant functor in C. I take the colimit when I indexed by S1, which is just BZ. Then I can split that into essentially three terms. One is S1 tensor K of C on the outside, and then there are two extra bits which are called nil terms. And this is a statement that holds for general localizing invariant. Maybe if you want to say Verdier localizing, you have to add the word idempotent complete to C, but I mean, this won't matter to us. So I call this Bass-Heller-Swan. You might also know this as the fundamental theorem in K-theory. And the reason I call them this is because you might have encountered this formula under a different formulation, right? If I have a spectrum, S1 tensor X is just X plus suspension of X. And if I start with the category that's of the form perf of R, so it's perfect complexes over a ring R, then S up to this idempotent completion business, S1 tensor perf X is just perfect complexes of Laurent polynomial in R. So this proposition, it's telling you how to compute the K-theory of Laurent polynomials. And it tells you, okay, there is one term that's just K of R, one term that's a shifted copy of K of R, and you might have two extra bits that come here, the positive and negative nil term. It so happens that if R is regular, these two vanishes, but in general, the best you can say is that there are those two extra bits. You can also get something for A theory if instead you specialize it to perf of sphere bracket loop X. So this picture here, it fits into a very general thing, which I'm not even going to explain here, which is something called Farrell-Jones. Farrell-Jones is still a conjecture, even though it's known for many groups, and it says the following thing. If you pick, so the one that I just want to explain, because it's the one that doesn't need you to modify a bit what I've explained before, is that you pick a torsion-free group, and then the conjecture states that the G-assembly map in K-theory is split injective. So this is what we see in the above picture, right? This splitting that I explained, it really is natural, it comes from the assembly map. And it's not an equivalence in general, precisely because there are those two extra terms that have appeared. Okay, so the assembly map in K-theory, it's nice to control the target because you have a map. So if K denotes the K-theory space now, there is the map from the largest subgroupoid of a category. Let's just pick a category, remove all the non-invertible arrow, and this is what is denoted with this upper script twiddle. And so in particular, every time you have a point in your category, you have a point in the K-theory space, and so it's easy to produce elements in the right-hand side. The left-hand side of the assembly is harder to control because it's a priori not the K-theory of something, so it's hard to map to. But there is recent progress that allows you to do this easier. If you have a stable category, small stable category, then you can int complete it. There's freely adjoined filtered colimits to it. This is now a presentable stable category. And this category of presentable stable categories, this object that's called PRLX, it's in particular dualizable. So this means that, I mean, there is a tensor product on PRLX that makes this a symmetric monoidal category. This is called the Lurie tensor product. And whenever I have a symmetric monoidal category, I can ask whether an object is dualizable or not. This is a property of an object. And I claim that in C is such a dualizable object. Now, all of the guys that are of the form in C are not all of the dualizable category, and this is somehow Efimov's big insight, is that it's still true that any localizing invariant extends to PR dual, which is this category of dualizable object in PRLX. And now the functors are not necessarily just continuous or exact functor. You ask for something stronger, which is strongly continuous, which equivalently is not only do they have a right adjoint, but the right adjoint preserves colimit. It has a further right adjoint. Right? This is a very important theorem. It tells you somehow there's not just K3 of small stable category that's interesting. There's a bunch of new objects for which it's harder to build the K-theory space, but it's still true that there is a well-defined value. And in particular, what's such an example of a dualizable category that's not necessarily of the form INSI, okay, compactly generated? Well, if you start with any dualizable category, so in particular, like say spectra, then you can look at sheaves on X, some space X, in the topological sense now, with value in C. This is in general very much non-compactly generated unless C is compactly generated and X is a very nice space, so like a profinite space. And it gives you a lot of very cool examples of dualizable categories. And it's even better than this. This sheaves on X with C, it's some sort of two-categorical cohomology theory. In particular, because K-theory is some sort of decategorification process, it maps it to an actual cohomology theory. So this is a computation that FMF does that's not that hard to make, which is that the K-theory of sheaves on X with values in C, that's just, so what I wrote K of C to the X, but this is just a way to say, this is the tensor notation, it's just cohomology with, I mean, if X is sufficiently nice, compactly supported cohomology of X with coefficients in K of C. So this is nice, right? It gives you a cohomology theory. Now remember, the assembly map was more of a homology theory, so we still have to do some to dualize this construction. But this has been done in unpublished work of Bartel, Efimov, Nikolaus. There is a recording of Thomas Nikolaus explaining this at some conference 2 years ago. I mean, I won't be using precisely this, but they're just a way to do the following thing, is to produce a map, which is this co-sheaves hat of X to C, which is a dual construction to sheaves. And this always maps to X tensor C, which in the presentable stable world is just functors out of X into C. This is a strongly continuous localization of dualizable categories. And if I apply any localizing invariant, so in particular like K-theory to this, I get the assembly map. So this is particularly cool because it means that, okay, if you want to understand the assembly map, it is the image of a map in K-theory, but you have to do dualizable categories. It's even better than this because this is a localization, a strongly continuous localization. The kernel in K-theory is the same as the K-theory of the kernel. So we know better than just the assembly map, we also have a model for its kernel. There's one thing we lost, however, it's passing to dualizable categories. We still only have a map from the K-theory space, into the K-theory space, sorry, but this map is not from the maximal subgroupoid of C, it's the maximal subgroupoid of compact objects in C. And the point is that if you have just a dualizable general dualizable category that's not necessarily compactly generated, you have almost no control on the compact objects. It could very well be that the left-hand side of this map here is just 0. So it's still hard to produce element in the left-hand side. So this is kind of slightly unsatisfying, right? You had to pass to a bigger category and you lost a couple of features. So the goal of the talk today, what I really want to explain to you, is that you could have had a different idea to make this work. Now this different idea in the case of stable category fails, but there is a slightly different context where it works. And this context is the context of what are called Poincare categories. So what's a Poincare category? It's a way to encode that there is a theory of quadratic form over rings. So in particular, you start with a stable category C, you give yourself a duality, or an equivalence from C up to C, whose inverse is its opposite. And I'm also going to require a bit more datum, which is I want a linear functor, so a functor that preserves either finite limit or finite colimits from C up to spectra. And I want even more data. I want to be able to glue the two kind of things that I gave you. So I want a map from this lambda of X, so natural transformation, to the mapping spectrum in C of X to D of X. Now this guy here, it has a duality because it's also the same thing as dx as maps from dx to x, and I want to take Tate C2 for the induced C2 action. Now the goal of all of this is to encode kind of a theory of forms. So quadratic forms, symmetric form, skew symmetric, and all of and many other things that you could imagine. And so I denoted C copper, and the reason is that the copper essentially, which is this pullback, right? If I give you this kind of data, you can pull along the map from homotopy fixed points to Tate, and this gives you a new functor, which I call copper, and it contains already all of the datum, right? If you want to recover lambda, you can just take what is called the first Goodwillian derivative. Universally enforce your functor to be an exact functor. If you want to recover the B kappa, which is this another name for map x dx, you just have to take the second cross effect. And then it's only condition on kappa that everything gives you like a Poincare category. The conditions are, I want my second cross effect to be exact in both variables, and I want my duality, which is a priori just a functor that maps into in C, to be a functor that from C up to C. So I want it to factor through the Yoneda embedding, and I want this to be an equivalence. So this is a lot of data. Also organize itself into a category. What are the maps in this category? Well, it's an exact functor from C to D, the underlying stable category. And I further endow them with a natural transformation. So I related the kappa, and the way I relate the kappa is just I have a natural transformation from kappa to the restriction of the other one that I call psi to along F. This naturally comes with a lax duality preserving map, right? I have a comparison between f of the duality and the duality of f, and I'm asking that this map is an equivalence. So I want that my functor preserves the duality. What are examples of Poincare categories? Well, one of them that will be very interesting to us is if you start with a stable category, you can always promote it to a Poincare category. The way you do this is you go C plus C up. Now this is equivalent to C up plus C, and so this is essentially the duality. It's just flipped to factor. And what I claim is that this data, like there is also a linear map and so on, and it's just like the pullback you get is precisely map C. And this construction is called the hyperbolic category on C. And so there's two things that I have to explain to you, is that all of these organize into a category called cat P. There is a notion of localizing invariant on cat P, which is essentially a very similar thing to what K-theory was. And there is an extra thing you can be now that you have the access to this, which is in some sense being purely about the quadratic form, right? If I have a localizing invariant on cat P, sorry, in some sense, I can, because of those hip guys, I can understand it has a behavior on stable category and a behavior on kappa. And I would like to forget about this fact that they have stable categories in there. So I'm going to ask my localizing invariant to be bordism invariant. The reason for the name, I don't really have time to explain. If it kills all of those hyperbolic guys. So in a way, a localizing invariant that's bordism invariant is something that cares not fully, but almost exclusively about the kappa. So what's an example of such a guy? It's L-theory. So L-theory is not quite localizing in this general sense, but there is such a thing as L-theory with the universal decoration that's localizing. So this is a functor that's one of its very nice properties, because we did this in such a generality. There is one functor and it captures all of the possible variants of L-theory. This functor knows about quadratic L-theory, symmetric L-theory, and all of those variants, and the only thing you have to change is the kappa. So for instance, it also means that all of those guys, they are not independent of one another. They talk to one another. And one way to make them talk to one another is to produce maps between them. So for instance, there is always a map from the quadratic kappa to the symmetric kappa, and this induces a quadratic to symmetric comparison map on L-theory. Okay. Now, inside Poincare categories, there are also some interesting properties that a Poincare category can have. For instance, I'm going to call an isotropic subcategory of C kappa. It's a co-reflexive full subcategory. This means the inclusion is a right adjoint. And I'm going to ask, so in the isotropy, is that this kappa vanishes on L. If this is true, then I have a fully faithful functor from hip to C kappa. There's always a functor from hip to C kappa every time you have a full subcategory, but now it's fully faithful precisely because the kappa vanishes. So in particular, the bilinear part vanishes. So this tells you that L is orthogonal to wherever its dual is getting mapped. So in particular, L and D of L are live fully faithfully in C, and I can ask some sort of a maximality condition on my isotropic subcategory. And this is something that I call having a Lagrangian. And having a Lagrangians precisely mean that your isotropic subcategory, if you take L and DL, they jointly generate C as a stable categories closed on the retract. Another way of formulating this is that the smallest subcategory of C that contains both L and DL is stable and closed on the retract is just all of C itself. And it's a fact that's proven, and I mean, yeah, maybe I should have said this, but all of this theory that I'm explaining here, it was developed in this series of paper by 9 authors, where they built the foundation of this were introduced by L-theory, but they built all of those notions of bordism-invariant and localizing invariance, proved all of the nice theorem in them, and one of those lemma, or proposition, is if I start with the bordism-invariant localizing thing, then it vanishes on every category with the Lagrangian. And the reason for this is quite simple. If you have a localizing invariant, it should not see the difference between hip-hel and C-kappa for everything that has a Lagrangian, but by the bordism invariant condition, it also has to vanish on hip of L. It also has to vanish on C-kappa. So this will be important for us for the following. And now we are ready to talk about the assembly map in the Poincare category context. So cat P is a very nice one category, right? It has all small limits and colimits, and they are preserved by the forgetful functor. In fact, the forgetful functor from cat P to cat X, it's a bi-Cartesian fibration. So computing colimits in cat P is not that hard. If you have a functor, you can just first take the colimit underlying, and then push all of the copas to the target of the colimit, and then perform the colimit in the categories of functor. So for our situation, the assembly map, right? You start with the Poincare category. You have a space X. The target of the assembly map is going to be X tensor C, equipped with some copas. And what is this copa? It's X tensor P shriek of copa. So here, P shriek of copa is the canonical map that goes from C to the colimit of the constant guy equals to C. And what I claim is that this is still an object in the category of functor, and I can take this tensor thing in the functor category. Now, what's the idea on trying to build the assembly map in Poincare categories? I told you already, right? The localizing invariant is a categorification of the passage from C to K0 of C. But we could also, in particular, the passage from C to K0 of C is itself a decategorification, right? You have something that's a category, and now you just have an abelian group, and you've forcefully split a bunch of stuff. So what I want to do is on the left side of the assembly, try to imitate the assembly map construction, right? The target of this, but one categorical level higher. The target of the assembly was some colimit, and so now I want to do something that's a two-categorical kind of colimit, and hope that this will be sent to the actual colimit by K-theory. And one thing is that all of this only works for spaces, right? If you start with a category, nothing happens because constant functor, they factor through the guy where I inverted all arrow, which is just a space. So this is some sort of strategy that is only going to work for spaces. But so let me instead let me explain what doesn't work, which is,
Can I ask a question?
sorry?
Hi, I wanted to ask a question. Can you
Yes,
go to the previous slide?
yes.
So this Gaussian hat
Yes.
thing,
The Kojif
this is
hat, yes.
this is what you said was in that unpublished work of Bartos, Efimov, and Nicholas, right?
Yes.
But I mean, so I mean, how if it is unpublished, how do we know what the construction was exactly?
I mean, this Kojif hats thing, it's built out of sheaves. So PR dual is a category that has an internal hom, and you can just look at the internal hom from sheaves to spectra. This is something called Cauchy's hat. And so because sheaves was some sort of two-categorical cohomology theory, the fact that you've put everything in the contravariant entry of the mapping spectra, or the internal functor object, it tells you that Cauchy's hat is a homology theory.
Okay, yeah, I see what you mean now. Sorry,
Right? It's
yeah,
purely formal from the statement about sheaves, essentially.
Okay, okay, I misunderstood you earlier. Yeah, because
It's,
when you
it's
said
just
it was
it's
fun,
just the internal uh, the internal object of PR dual is an extremely complicated thing. It's a very complicated dualizable category. So it's very unclear what concretely is happening in this guy. But it has the correct properties by some sort of abstract nonsense thing.
uh,
Um,
mm,
but I don't want quite to copy Koshif's hat precisely because of this issue. There's another thing you could do. And this other thing is called oplax colimits. So what's an oplax colimit? Well, you have to use the fact that catex is not just a one category, it's a two category. In particular, I can ask them not that triangles commute, I can ask them to be prescribed some natural transformation. That doesn't have to be invertible. And an oplax colimit is just, I start with a diagram, and instead of enforcing that I have a cocon, I enforce that I have a lax cocon or an oplax cocon, depending on which direction the natural transformation is supposed to go. And the universal such guy I call the oplax colimit. Uh, what is the oplax colimit of a functor in cat, right? Before doing catex? Well, it's just its co-Cartesian unstraightening. And if you remove the word up and you just do lax colimit, then it's going to be its Cartesian unstraightening. I mean, and you can check, right, that if you have a map from inside of the source of this functor, from I to j, the inclusion of the fibers, they don't make a commutative triangle to the unstraightening. They make a lax commutative triangle, and the laxness is precisely the fact that you have a co-Cartesian lift pointing in one direction. Now, what happens is that, I mean, in similar fashion to the fact that stable categories are closed on the limit but not colimits in cat, even if you start with an exact functor which lands in stable categories in exact functor, it's not true that the co-Cartesian unstraightening is stable. But this is not a problem. You can always force it to be stable in a way that will make it the oplax colimit, which is force the inclusion of the fiber to stay exact inside of UNF. Inside of each fiber is a stable category, and I want that all the exact sequences in there, they stay exact sequences in whatever the oplax cocon is. And I'm going to give a name to this oplax colimit of f in the stable world. It's unx of f, this guy at the bottom here. So this is the oplax colimit of f as a functor from I to cat x, let's say. And now I can start with the functor to cat p, and I might want to do the same thing. And now cat p compared to cat x is a significantly worsely behaved category, right? Cat x is a very nice two category. I said cat p was a very nice one category. It is, however, a very poor two category. The reason is we've asked that things were duality preserving, and we've asked that the duality were equivalences. These are very one categorical constraints, not very two categorical, and so they interact poorly with this idea of oplax colimit. Now, we could still try to do it, and it's going to work, but we have to somehow first enlarge what we mean by cat p. So I want to produce an oplax colimit. We expect that the underlying thing will just be the oplax colimit of the stable guy. So I just have to produce to you some functor kappa. And in like this category of SP is just a one category. Quadratic functor to SP is also one category. There's never going to be any room for oplax things. So the only strategy you have is, okay, pick a functor to cat p. Then you have a bunch of kappas which are defined on each fibers. Right? F of I is a stable category equipped with some kappa that I call kappa I. And what I claim is that all of the left can extension of those guys to the target, right? You have Coco map. Then this is an actual functor. A priori, it's only oplax, but precisely because of what I explained before, it's not. There is no room for the oplax things. They all become equivalents. And then I mean, if I have a functorial diagram, I can take its honest colimit, and I get something that I call UNH of f, which is not a Poincare category, but almost. It's a stable category equipped with a functor that stays two excisive, so it has this property that the second cross effect is exact in both variables. but we've completely lost the fact that the duality was an equivalence. So it's only an object in something called cat H, which is a bigger thing, which contains all of the Poincare categories. But in cat H, there's no need for the duality to be an equivalence, and there's no need for the functors to preserve duality. In a sense, cat H is the version of cat P where I removed all of the conditions that were very one-categorical in essence, and I kept only the two-categorical things. And so the oplax colimit, it really naturally wants to live in this bigger guy, because it's really a two-categorical thing. And even if I start with the Poincare, functor to Poincare category, it's not true, and there are very easy counterexamples that this UNH of F is a Poincare category. This does not work. What is one such counterexample? Just pick, so I is delta 1, and F is constant, so it's just you pick a category, which is the Poincare category. This should probably read C kappa. Then you can check that this UNH of F, it's supposed to live over the arrow category. The arrow category is the oplax colimit of a constant functor equal to C indexed by delta 1. But the hermitian structure you get is just, if I give you an arrow, you pick the value of the kappa at the target. In particular, this means that the duality has to pick an arrow and send it to 0 to d of y, where d is the duality on C. And this has no chance of ever being an equivalence, right? It completely forgot about the other half of the arrow. Like, it doesn't know about x. So this doesn't give me a duality, and so it's not a Poincare category. Now there's one thing that works still in the above thing, right? Is that the duality still is non-degenerate. It doesn't land in the C, it only lands in C. This is already a phenomenon that is very helpful, and it comes from the fact that I is a very finite category, like this delta 1. So what we prove in the paper with Jordan and Guglielmo is if you have a strongly finite category, so it's finite as a category, like finite obtained by push-outs and co-products out of star and delta 1, but we also want it to be enriched in finite space, so really a categorification of finite things. Then the duality on this Hermitian oplax colimit, it's always non-degenerate. It always only lands in C and not necessarily in end of C. Now, there is a miracle that happens, and the goal of the talk is to explain to you now the miracle. Like, the general oplax colimit business doesn't work, but if you start with not any category, but pick a finite simplicial complex and look at the category which is the opposite of the poset of faces. And so if you have a simplicial complex, the faces are included into one another. You can look at the poset of this, and I want to order it for the reverse inclusion, right? I want the, if a face is inside another face, then I have a map the other way around. Then this has, like, the miracle is the following, is that any functor to cat P whose source is this precise shape of diagram, right? The opposite of poset of faces of a simplicial complex. Then this UNHF Poincare, Hermitian category that I define, it's automatically Poincare. So what is happening there? It's because the shape of this poset of faces is extremely self-dual, right? One of the things that didn't work for delta 1 was there was no way to somehow dualize the thing in a nice manner, but for posets of faces of simplicial complex, right? So for instance, the simplicial complex delta 1, which has 1.0 and like 2 points and 1 arrow, its poset of faces is the twisted arrow of delta 1. And so this is something that looks like I have a point and two maps, so it's a cospan. And more generally, you have if you do this for delta n, the simplicial complex delta n, then the poset of faces is twisted arrow of delta n. And all of these are a lot of duality, right? Because here I can just flip the 0 and the 1. And actually, the proof of this theorem is precisely just this, right? If I have a simplicial complex, it's glued from its faces, which are of the form delta n. And this construction that I presented to you, it's an oplax colimit. It should commute with colimits. So in particular, if you just are capable of proving that for k being delta n, this is true, then this extends. Now, one of the reasons we are able to prove this is because that when you have when your source is delta n or a twisted arrow of delta n, or more generally a sufficiently finite category, there is another model for UNH of f than the abstract thing that I described. It's pick the underlying, like the underlying thing is the category of section of a Cartesian fibration. So right, if you have a functor from phase k up to cat x, you can just to cat, you can unstraighten it. And this happens to be a model for the underlying stable category of UNH. In particular, it's automatically stable, which is a bit surprising. And what does the kappa do, right? I mean, I've told you about a stable category. To make it a Poincare category, I also need to tell you about a kappa. The kappa picks a section. So this is some sort of a system of xi for points in each faces, in each fibers. And then I just take the colimit. And the claim is that this is functorial and everything here works. The reason this works is a very nice phenomenon. This category of section, it's actually the oplax limit of f. Right? I mean, I've told about oplax colimits and how they were annoying, that oplax colimit of stable category weren't necessarily stable. Well, the limit case is much better behaved. Oplax limits computed in cat or in cat x, that's the same. And it's this two-categorical phenomenon that's very similar to the fact that pullbacks of stable categories are stable even when they're computed in cat. Now, this only works for strongly finite stuff. And this is precisely what the strongly finite stuff appears. Sorry. Right? This fact that in cat x, the oplax limit and the oplax colimit are the same, it's some sort of lax semi-additivity, right? I mean, inside cat x, right, on stable categories, you know that co-products and products go inside. Well, here, essentially, I'm trying to describe to you a categorification of this phenomenon. Now, this categorification only works for finite things, essentially because it works all the time on presentable things. This is where, for instance, in presentable things, colimits indexed by spaces, they're the same as the limit indexed by spaces. The reason for this is that how do you compute a colimit in this PRL? Well, you just pass two adjoints everywhere. This gives you a diagram that has now a limit, and I claim that the limit is now the colimit. Of course, if you are a spaced index diagram, all of the map are invertible. Passing to the adjoint does nothing, and so the colimit and the limit are the same. More generally, it's true that in PRL, oplax colimits and oplax limit coincide. And this strong finiteness condition, you can also think about it as a sufficient condition for this very nice phenomenon to descend to stable categories. Okay, now I described to you a miracle. It's still not that miraculous. Nothing is like perfect. Even in this situation where I start with I being the poset of faces, the opposite of the poset of faces of a simple complex, it doesn't have to be that all of the canonical maps of the oplax cocon are duality preserving. Differently said, this UNH of f, it's not the oplax colimit in cat P, because the oplax cocon that defines it is not inside cat P. It's only a miracle that the target happens to be a Poincare category. In fact, a more general statement is true. The only maps like Fi to UNH of f that are duality preserving are those that correspond to the inclusion of zero simplices, like a face of dimension 0. And if you like try to include a k face into UNH of f, what you see is that it actually shifts the duality by a factor of k. Okay, so this was oplax colimit, and now I claim we have everything we need to build a model for the source of the assembly map. Right, so why is this? Okay, if you start with a simplicial set, right, the space associated to it, right, to a Kant complex, it's the same as a geometric realization of the poset of faces. But now oplax colimits are very functorial. So if I give you a functor out of the geometric realization of a poset of faces, there is a map from face k up to k to geometric realization of k. I can pull along this and it will induce a map on the oplax colimit. Now, because the functoriality is only nice for hermitian category, this is just a functor between, it's just a hermitian functor. It doesn't have to preserve the duality, but it so happens that the kernel of this functor is always stable under the duality. And now this functor is not any functor, it's the cofiber of its fiber. A different way of saying this, which is a bit more concrete, is that this functor is a localization, and the kappa at the target, the quadratic functor, it's left can extended along the inclusion of this to this. This formally implies that this functor is a Poincare functor. Why is that? Is because Poincare categories, they're closed on the colimits in hermitian categories. So in particular, if the fiber is the inclusion of a category inside another, with the restricted kappa, then this is a Poincare functor. This is precisely this fact that it's stable under the duality. And now I take the cofiber of a Poincare functor, I still have a Poincare functor, and so this is a Poincare functor. So this is a rather formal argument, or rather the second part, right? This fact that it's the cofiber of its fiber, it's extremely formal. Face k up to k, that's a localization. And so the localization, they are very much related to colimits. And so the induced functor on oplax colimits, it also is a localization. One way to see this is to see that to descend along oplax colimit, it's sufficient to invert all of the maps in the diagram that will become equivalences. Now, however, the fact that the kernel is stable under the duality is a significantly more technical statement. And the core strategy to prove this is to prove that the duality is an equivalence. This is a local criterion. What I mean by this is that duality is an equivalence if and only if at each x, the map, the canonical map from x to the double dual of x, and I just need that this map is an equivalence. This is sufficient to prove that D is fully faithful, but because it's its own adjoint, it's also going to be, like if your adjoint is fully faithful, you're a localization, and a fully faithful localization is just an equivalence. In particular, it's sufficient to prove that the category is Poincare to check that every x is in the image of a duality preserving functor. And so this is what the strategy implements, is that if you have a simplicial complex, it's built out of delta n's. And now you just need to check that something on delta n, like the kernels on delta n, they're all stable under the duality, and so they induce duality preserving functor onto the kernel. And this is an instance of this two-categorical homology theory that I was talking about on Cauchy's hat. Except now I don't have to do Poincare categories, right? This is just the following fact, right? If I give you a simplicial complex and I realize it as I have added some face delta n to a L, right? It's some finite simplicial complex L prime, and it's obtained by pushing out, so gluing a delta n to L. Then I claim that any functor from the positive faces of this glued guy, L prime, it fits into a push-out square. So the source is the oplax colimit of the functor restricted to the faces of K. And I mean, each guy here is oplax colimit of F restricted to whatever it has to be restricted from. And this is better than this, right? Because delta n inside L prime is the inclusion of a face, and so is K inside L. The vertical legs in this guy, they're all kernel inclusions. And this is a two-categorical phenomenon, like a two-categorical version of a homology theory, right? This is, I mean, in a sense, this is the axiom that tells you that it sends, I mean, here it's push-outs to push-outs, but it very much is the spirit of it. So this theorem, it also has for consequence that the kernel have to map to one another and exhaust one another. So every time you pick a point, it has to, and it's in the kernel, it has to be mapped by the image of some delta n. And because it's hit by some delta n, it suffices to check that the kernel for this specific case, k equals delta n, are stable under the duality. Now this is, I mean, just a computation. You have to now understand what the kernel looks like and look inside of it and check that indeed the duality does what it's supposed to do. I don't think I have any insight to bring here. But the upshot is actually much better. If you do the calculation correctly, you will find out that in delta n there is a Lagrangian. So there is some sort of maximal subcategory of K that you can write, and together with its dual, they generate the whole kernel, and the kappa vanishes on all of those guys. Now this is very cool, and this is somehow where the magic happens. If you have a bordism-invariant functor for k equals delta n, right? Because the kernel is now Lagrangian, this map is automatically an equivalence. This is telling you that the oplax colimit of f applied at E is just f of the point, which looks very uninteresting. But because of all of this two categorical thing that I've explained to you, right, the left-hand side here, it has all of the nice naturality property, and I know for the delta n that it glues to the correct value. And this form, now this, it's a purely formal thing to see that the left-hand side, generally for any k, is a model for the assembly map. Right? You have a localizing invariant. So sorry, yeah. If I go back to this square, if I apply a localizing invariant to this square, it stays the push out. And now I know that for all of those guys here, I have the correct value, and everyone here is glued out of delta n. So every finite simplicial complex, right, is glued from delta n. I have the correct value on the generators. Therefore, I must have the correct value everywhere. And so this is the claim that I now make, is that, sorry, it's missing a f here, is that this E of phi k, from the oplax colimit to the colimit, it's a model for the assembly map. Differently stated, this left-hand side guy, right, you can replace Cauchy's hat by this guy. It's also some sort of two-categorical homology theory. So one nice property of this is that in particular, because the left-hand side of the assembly never really depends on anything else than the space k, even though here it looks like I had to choose a finite simplicial complex k that realizes to k, actually the value under any localizing invariant doesn't depend. Another thing that also generalizes rather straightforwardly is that if I now assume that my E preserves filtered colimits, then I don't really need this finiteness hypothesis anymore. This is just now more generally true that this will be a model of the assembly map for all simplicial complexes. Yeah, so this is the theorem. It has an extra thing, right? Is not only did I have a functor that models the assembly map, I actually got to build it as the cofiber of its fiber. Another way of saying this is that E of this functor, E of the fiber sequence associated to this, it will stay a fiber sequence after applying E. This is this E of the kernel is the kernel of E. And so in particular, I gained a model not just for the assembly map, I also gained a model for this E of ker phi k. This is a priori very cool. It means that, okay, if you want to understand whether the assembly map is an equivalence, right, you just need to check that this vanishes. Need to be careful here, right? I checked that for delta n, this worked by showing that there was a Lagrangian, right? But this is not a property that's stable under pushout. Essentially, it's because duality preserving map don't have to map Lagrangian to Lagrangian. It's a condition on the functor to preserve the Lagrangian. So it's not like, don't be fooled by this, right? It's not true that L-theory commutes with arbitrary colimit of spaces. This is not what it proves, right? It's now like the strategy that we employed to check that ker phi k vanished for k equals delta n, it will not work generally for non-trivial shapes. In particular, it means there's now more work. Like if I want to check this Bass-Heller-Swan thing in the Poincare case, I still have to prove to you that if I start with k and S1, find a finite simplicial k, write a finite simplicial complex that models S1. All of those Lagrangian that I've described, they do glue to one another. But this is something we can do. We check in the paper. And the consequence of this is that you get L-theoretic Bass-Heller-Swan. And it's even better than this, right? Because the assembly map is just an equivalence. There is no nil terms that can arise, right? And so here I'm doing it for the constant functor, right? This is the above, but when f is constant. But you don't even need this, right? This works in full generality for any f, so you can twist by any duality-preserving automorphism that you want. And let me conclude. And this is the extent of the computation and the things that happen in the paper, but you might be wanting to do more. I had to restrict for all of this to bordism-invariant functors. What this is kind of sad is that I don't really have a good model for things like K-theory or GW, which are not necessarily bordism-invariant. And it's clear that in my strategy, right, I really relied on the fact that for the points, for delta n's, the kernel vanished. And the only reason I could prove the kernel vanished is because it had a Lagrangian. But in K-theory, this will not tell you that anything is zero. So now that, and this is something that I don't know how to do, but I really would like to do, is that be able to do this by removing the hypothesis bordism invariant. Change a bit what plays the role of the oplax colimit, so that it still has this two-categorical homology theory feeling, but it doesn't require that the kernel is a Lagrangian. Another thing you could try to do from this point of view is now you have an explicit model for the kernel, and there's a conjecture that tells you, okay, in L-theory we expect the assembly map to be an equivalence very often. Pick your favorite model for the space where this is supposed to happen and try to compute the kernel. Can you see whether it vanishes or not? This is usually very technical. I don't think there is a lot more to be said, but this is probably worth at least investigating a little. And maybe the better way of doing this is checking whether there's some inheritance property of this kind of Farrell-Jones conjecture that hold, right? Farrell-Jones is known for a lot of groups, but there are also a lot of inheritance property that are known for these groups. And so it's probably interesting to try to see if you can find, like, first of all, reprove all of the old statements in this context, and also prove the maybe new or more intricate inheritance property from this. And this is all I had to say. So thank you very much for listening.
Thank you, Victor. Let's unmute ourselves and give the speaker a round of applause. Okay, if you have any questions, please ask them. I was wondering, like you ended with these with a small comment on Farrell-Jones. So this is a Farrell-Jones question, basically. So I was looking in Sasha Efimos' recent paper there. He had this equivalent statements for like all what was it?
Yes.
Like all C and cat per PG satisfying Farrell-Jones. He had some like generation property related equivalent statements to this statement. So with your, I mean, assembly map work, can one hope for, I don't know, more equivalent statements to those statements?
I mean, so what
Along with,
Sasha does is really in the case of stable categories, and so um, all of this really, like, I mean, bordism invariant doesn't really make sense for stable categories. So the answer is yes, but you have to do a lot of Poincare categories, motifs in Poincare categories. You also have to do, I mean, one of the way he implements this kind of like statement is by looking at not just stable category, but stable G categories, right? So categories of the G action and doing motifs there. And so you also have to do this with Poincare categories. And so somehow here the framework is more of the kind, I start in cat P and I just look at the guys there, whereas he's looking at a bunch of different categories, which are just like functors from BG to cat X and doing motifs there. In the sense is it's almost like he's saying, okay, to prove Farrell-Jones for K-theory, let's prove Farrell-Jones for motifs.
yeah,
Motifs being a categorification of K-theory, and so if you expect that some statement about Farrell-Jones is true for K-theory, it will true for the thing that universally like categorifies it, which is this motifs. So yeah, I expect that similar statement should hold for L-theory and like the bordism invariant motifs, but this is probably hard to prove and maybe out of reach for now. I don't think the methods that we used here can tell you this kind of things.
okay.
Yeah, I think somehow like wait, can you hear me?
Yes.
Yeah, yeah.
Yeah, I think somehow like it seems that for all these categories of motives, which are kind of built from stable categories, from certain like functor categories to stable categories, like motives for G-equivariant things, these somehow behave like much more like sort of usual local non-commutative motives than the category of like Poincare motives or like these bordism-invariant motives. They have like a very, very different flavor. I mean, yeah, even just manipulating the basic categories is much harder in the Poincare case as the stable case, right? You have like 3 auxiliary functors floating around and a duality and C2 action fixed points, ops everywhere. It's not quite as smooth.
Okay, thank you. Any other questions for Victor?
Maybe also just a comment, by the way. You brought up the Cauchy's hat stuff on the level of like dualizable categories, but maybe there's a simple example of this kind of thing that people might be more familiar with. Namely, like, how can you learn something interesting about, let's say, K theory by going through some kind of like lax limits, just even restricted to stable categories. And I guess the main example is like the Land-Tamme paper on the K theory of pullbacks, right? You form like this lax pullback, and then you identify it. You identify it with like some category of modules, and then that gives you like an interesting like localization square for stable categories. Now, I guess people are very interested in studying like pushouts and pullbacks of rings, but when you start doing like geometric topology and you start involving L theory, like the assembly map for groups is kind of the main goal basically. And so here, I think it's interesting that we've managed to use similar results to kind of do Land-Tamme style stuff, but for these like much weirder spaces and for like more exotic invariants.
Yeah, thank you. I didn't realize how complex it was. Any more questions? Victor, let me just, this is probably, I mean, you did deliberately say, you did say that you didn't want to say anything about this earlier. Why the term bordism invariant?
Sorry, can you say that again?
Why is it called bordism invariant?
Sorry, I can't hear you. Can you speak louder?
Why is it called bordism invariant?
Ah, uh, I mean, this has to do with sorry, right.
Sounds fine.
This, I mean, it has to do with the fact that so how do you build, for instance, GW on cat P? You build those categories of like this twisted arrow category of delta n, and you tensor or sorry cotensor your Poincare category with those, and these are the Q construction. It so happens that all of those QN categories, they have a isotropic subcategory, which is just C. So in particular, they have a map from hip C, a fully faithful map into hip C, and the cofiber of this is Qn minus 1. So if you think about those Qn guys as categories of cobordism, right? Because they are categories of cospans, then being bordism invariant is just not seeing the difference between C, bordisms, no, cobordisms in C, and cobordisms of cobordism and cobordisms of cobordism, right? Because you kill the only difference, this hyperbolic guy, between the Qn and the Qn minus 1. Qn minus 1 being cobordisms in Qn. So this is why it's called bordism invariant, is because it's somehow in the Q construction, it's really killing all of the differences. Like the Q construction now becomes a constant simple object for those guys.
Okay.
So another definition of bordism-invariant is precisely those for which, when you apply the Q construction to them, you get them back.
Okay, thank you. Any questions, anybody else?
Maybe just a comment as well, like in the whole like 9-author paper setup, GW, which is like the more fundamental invariant, is defined basically like kind of in terms of the Q construction. And then L-theory has this like seemingly weird definition with some other kind of like construction, the row construction. And the point of that is precisely to kind of like approximate GW by something that is then forced to vanish on these hip things. And that's what gives you L-theory. Yeah.
Thank you again. Right, if we don't have any more questions for Victor, let's thank him once again. Can you send to me afterwards the slides you used?
Yeah, of course.
Okay. Good to see you, and good to see you too, Jordan.
Yeah, it's really nice. Thanks again, Victor.
You're welcome.